Hello everyone. Welcome to ChemCore Organic Chemistry. This chapter will focus on the final branch of isometry, stereochemistry. Before we talk about the central concept of stereochemistry, we should define what stereochemistry means. Stereochemistry refers to the branch of chemistry concerned with three-dimensional arrangement of atoms and molecules and the effect of this on chemical reactions. In other words, by studying stereochemistry, we study how stuff is organized in 3D space. We already know how this works, the wedges and dashes we've been drawing. In this chapter, however, we will really focus on how these wedges and dashes are organized and what they really mean. Here's an example of why this chapter is so important to the study of organic chemistry. Our bodies are specific to certain molecular stereochemical arrangements, and having the wrong stereochemical arrangements could have dire consequences. In the 50s and 60s, a new drug to treat morning sickness for pregnant women was created and deemed safe for humans to use, called thalidomide. Did it get rid of the symptoms? Yes. Did it cause other stuff? Also, yes. But why? It turns out that the people creating thalidomide did not consider stereochemical arrangement of this carbon, termed a chiral carbon. By mixing the two different 3D arrangements this carbon could have, pregnant women taking this drug had children with severe birth defects. In summary, one stereochemical arrangement was a great drug, and the other was a toxin to fetuses, or a teratogen. The concept of stereochemistry can be illustrated by your hands and feet. Look at your palms like I am. It should be visible to you that your palms appear as mirror images of each other. However, if you superimpose your hands on top of each other, they're not the same. This also happens with your feet. Your left and right shoes are mirror images. But if you try to wear your right shoe on your left foot, it'll probably end up being uncomfortable. Why? Because your feet are not superimposable. This translates to the first type of stereoisomer we learn in this unit, enantiomers. Enantiomers are defined as mirror images of one another that are not superimposable. For instance, this molecule on the left is mirror images with a molecule on the right. However, we are not able to superimpose them. Therefore, they're enantiomers. In general, to draw an enantiomer, we can literally just draw the mirror image and keep everything the same. However, there is an easier way, and learning how to use this method to draw enantiomers will become extremely useful later. Here's another example of enantiomers. To review, we placed a line of symmetry between these two molecules to generate a non-superimposable mirror image. But what literally happened? By making a mirror image, we literally just flipped the methyl and hydroxyl groups. Why didn't we flip the bromine and chlorine? Well, remember that bromine and chlorine go out and into the plane of the paper, while the lines of symmetry we drew is in the plane of the paper. Therefore, we don't flip the bromine and chlorine. It's useful to remember that by making an enantiomer, we could draw a literal mirror image, or we can take any two groups and flip their positions. By making one flip or an odd number of flips, we generate enantiomers. But what happens if we make two flips? As you can see by the new image on the right, the mirror image of the mirror image is literally the same original molecule. This concept will become super important in a later video, and will make certain concepts really easy. I want to summarize this video with a definition of a chiral center. A chiral center is any carbon that has four groups attached to it. Every chiral center, and only chiral centers, require stereochemical specifications, like wedges and dashes. It'll be incorrect to draw wedges and dashes to a carbon that is not a chiral center. In the example we had previously, the carbon in the center is a chiral center, while the methyl group carbon is not. This is because the center carbon has four different groups attached to it: bromine, chlorine, methyl, and hydroxyl. However, the methyl group does not have four different groups attached to it. Molecules that contain chiral centers are called chiral molecules. We'll soon talk about an exception to this rule, but the definition of a chiral center is useful to remember. This video covered the concepts of chirality and enantiomers. The next video will cover the concept of designations for chiral centers. Practice the concepts using the free worksheets and answer keys linked in the description below. See you guys in the next video.